Okay, we're going to pick up with our next piece of this lecture, and we are going to finish talking about circuits, and then I'm going to do a separate video on my fancy new iPad about how to do these circuit problems. So we'll kind of get through the theory first, and then we will finish up with a set of problems in a separate video. So we already talked a little bit about meters, and so the main thing is when we're working these problems, we're going to assume that we're working with ideal meters here. So if we do that, then we'll know that we are using the like we talked about with the infinite voltage for the voltmeter and the zero voltage for the ammeter. Okay, so when we talk about these meters, we're going to be measuring different things in these circuits, and we talked about Ohm's law already. So we can measure voltage, we can measure resistance, we can measure current flow, but also we can measure power in a circuit. So when you look at the power in a resistive circuit, then there's different ways to calculate it. Now, for an ohmic circuit or one that obeys Ohm's law, there are particular formulas that you can use, but the general formula is always related to the work done on a charge. So we talked about the work done to move something through a potential difference in unit 2, and we saw that that was the charge that we were trying to move multiplied by the difference in potential. And then you have to remember from physics 1, the definition of work or power is work per time or energy per time. So if you divide that out, when you take charge and divide by time, that's current flow. So the definition of power is always the current flow times the voltage difference or the potential difference. But for an ohmic circuit, we can replace that in Ohm's law. So if we put in Ohm's law, we can get different ways of writing the power equation by substituting in for I or for V from Ohm's law. Okay. So when we talk about different types of circuits, then we're going to be calculating things like the power, things like the resistance, the total resistance, or the current flow, or the voltage across something. And we'll have several examples of that in both the homework video and also in the video where I show you how to do circuit analysis. So when we talk about something being in series, what that means is they have one end in common. You can think about the current flows through something and it only has one path, so it has to go through everything sequentially. So what that means is in a series circuit, all parts get the same current, but different things have different amounts of voltage depending on their resistance. So sometimes this is called a voltage dividing circuit. It has a constant value of current because the current has to go through everything because there's only one path, but it divides the voltage up depending upon the resistance of the individual elements. So you can have a circuit that is all series. You can have part of a circuit that section happens to be in series. So depending on what you're analyzing, you can look at different pieces of the circuit. So if we apply Ohm's law to each part of the circuit, and I'll show you that analysis in the next video, you end up with an equation for the total resistance that looks like the following, which is embarrassingly small. But it's the total resistance is, you just add up the resistors, and we'll look at some of those in the next video. In parallel, what happens is you have multiple paths for the current to flow through. So it comes into a point and then it splits into different branches. So when we do that, then in that case, if you have something that's in parallel, the parallel section, if you're measuring across it, you're going across everything, so all the parts of it get the same voltage or the same potential difference, but the current splits up through the different branches. So in that case, it's called a current divider. The total current in has to equal the total current out, but maybe part of it goes here, part goes here, and part goes here. It splits up in the different branches. So again, you can apply Ohm's law and derive your expression for equivalent resistance. And again, it's embarrassingly small, but we'll look at that in the next video. Now, if you have a circuit that you can't break up into series and parallel pieces because there's a battery that gets in the way, in other words, it might have more than one battery or more than one source of potential difference, then you have to use something called Kirchhoff's rules. We're also going to see that in the analysis video that will follow this one. So it lets us analyze a circuit in a fairly straightforward way by using a couple of rules, all right? It looks at the conservation of both voltage and of current. So we talked already about a potential pump, a battery being a potential pump. And so when you go all the way around a circuit, like we talked about the garden water feature, when that water ends up back at the same place that it started, that means its change in potential energy was 0. So the same thing is going to be true of these charges. So if we analyze a circuit and we go all the way through the loop of the circuit and we start and end in the same spot, then we're also going to have 0 change in potential energy. But that's going to be because we have 0 change in voltage if we start and end in the same spot. Same thing with current flow. Current can't just hang out in any part of the circuit. It has to flow in and flow out depending upon which direction it's going, but it can't linger, say, in a junction. So the amount of current into a junction has to equal the amount of current out of a junction. And so those are things called the junction rule. The junction rule is the first one. It says the algebraic sum of any currents in a junction is 0. So we're going to take currents flowing into a junction as positive, current flowing out of a junction is negative. And we'll talk about how we assign that when we get to the analysis part. So what that means is in plus out has to equal 0. Okay. So again, my equation is tiny there, but it's I net equals 0. So the junction rule says I net has to equal 0 at a junction. The loop rule says the algebraic sum of the voltages around a loop has to be 0. So I'm going to have voltage increases and I'm going to have voltage decreases, but if I start and end in the same spot, they have to add up to 0. So what that means is you add up everything that creates potential, and that should be add up, not all up, but add up everything, and then it has to add up to 0 if you start and end in the same spot. The trick here is getting the signs on things correct. So we're going to assign sign conventions. Like I already said, current flowing in is plus, current flowing out is minus. That's my decision. They have to be opposite signs. You can do it different, but that's how I'm going to do it. For batteries or sources of EMF, they have a positive post and a negative post, and we'll talk about that in the analysis video. But as you're looking through the circuit, as you transverse the circuit and you figure out how you're going to work around it, the sign of the voltage is the side of the battery you come out on. And that'll make more sense as we look at the analysis. But if we come out the positive post, it's a plus voltage. If we come out the negative post, it's a negative voltage. Now for resistors, since we're talking about conventional current, current is going to flow from high potential to low potential. So the current flow through the circuit indicates the direction of decreasing voltage. So if you're analyzing the circuit and you're going around the analysis with the current flow, that's a drop in voltage. And if you're going opposite the current flow, that's a rise in voltage. And you'll see that in the analysis video. And then you just add them up using Ohm's law for the resistors, and then whatever the voltage, the terminal voltage of the battery is. Okay, so this will make a lot more sense when we get to the next video on analysis.